Hi, this is Vincent Borbely for CSC 386's fourth assignment. First part was doing capture the flag network. So just to start here, I'll start running it just because it can run for really any amount of time. But as you can see here, they both run in sync and they're only moving individually based on the results of the coin flip being sent in between each other. So I'll get into that in a little bit, but to get into the game here, we included this action function based on move data. It just moves the appropriate player based on the data passed in. To look at my network manager, we changed a little bit. The enum here has now types for both players' coin flips as well as both players. So that's what goes in packet header now. Send message and receive message with ACK. There's not too much to talk about here. I just didn't really do it last time. So it has, for example, send message with ACK sends the message, handles acknowledgement, as well as duplicate packets. So it may not be super clear to see here, but every so often it'll duplicate a packet. It handles that appropriately. Um, to look at it in more depth, I believe it's 10% on both ends now as it's running. So looking at main here for the game itself, I should look at client, excuse me. Client, or otherwise known as player one in this situation, would get a coin flip, send that coin flip over to player two, wait to receive player two's coin flip, and then compare the two. And based on the results of both coin flips, it would do the appropriate action. And then update the board as usual. Player two kind of does just a little bit different order of that same shtick, but otherwise, as you can see, it works. And in a little bit, we'll cut back to it when they win. So now, some 500 ticks later, we have a winner finally. Their positions, both players on both sides, have remained synced. They pass memory tracking, and there's no errors on either end. So I'd say we successfully done capture the flag. Now, when it comes to data driven, first we wanted a calculator with set, add, subtraction, multiplication functions. Nothing too crazy on this end. I have all that. Of course, later we would edit it to have calc data. So you would make a calc data, set it to an action that you wanted it to do with a value, and then calculator would do work based off of that data. So we have both the enum for actions that you might want to pass in, as well as the calcdata class here. So you can set its type and value. And then calc itself has a do work function where you pass in data. It takes the value and does the appropriate action based on the uh, the type of the data passed in. So nothing crazy there. FSM then. Um, Actually, before I move on to FSM, this will all work. I'll demonstrate in a bit here. FSM was a little more advanced, to say the least. I'm not sure if I did it entirely correctly, but FSM, it has an FSM state enum. FSM itself can be set to any one of these states that it has access to. It advances based on a byte, so it talks to its state, tells it to advance based on that byte. Every state that it has derives from the base state class, and then each of these states goes in whatever direction it needs to based on the byte passed in. Similarly to calc, it also has FSM data, which had to be done a little differently because now we're being asked to set advanced data as well as state data. So these also derive from a base class, the FSM action. So we have advanced action and state action, and they do about what you'd think they'd do, which is advanced based on a byte or set state based on the state passed in. And they have these general execute functions so that later when tests, oh, excuse me, I didn't mean to pin that, but when tests would then go down the line and enqueue all these things and process them, we could say uh, when FSM does the do work, we can then call this execute function and it would execute whatever work it needs done. Lastly, for the interleaved, so interleaved required an input queue here. So I have a queue. It can add either calc data or FSM data to it. This also required new messages to be made. So I made a base message class. They derive from that base message class. They do everything they should. They have, like before, necessary execute functions. And that way, when they're processed, you can go through and just call for each one to execute its appropriate action. So if I play it here, of course, it goes through without a hitch. And if we compare just interleaved really to the results given here, the sample output, it looks to be about the same. So I'd say it's a successful assignment.